Hello, and welcome to my first video. This is going to be a video in a series that I'm doing on general chemistry. Qualifications, as you might suspect, are that I did really well in chemistry. I teach chemistry, I'm a tutor, but more about that at the end. And I think the main focus of these videos is not necessarily to give you a full overview of chemistry, though there will be some of that here. Rather, is to present some of the more difficult concepts from the college and high school level course, although with a focus on the college level course, in ways that are simpler to understand, or perhaps the ways that I came to understand them as a student myself, and the ways that have worked the best when I'm teaching my students. Zoom in. Unprofessional. Okay. So brief overview. This video is called Putting Electrons in Their Place. It's going to be part of a 2-video series that will eventually lead us into periodic trends. For a quick overview, I did number 1 already, kind of. But we're going to talk about the purpose of these videos in general, the Bohr model, beyond the Bohr model, and then what the implications are and where we're going next. Okay, let's get started. So, why are you here? Why am I making these videos? As you can see, it is your professor's job to give you knowledge, facts, things to memorize and learn. I see it more as my job to give you understanding. I want to guide you as someone who has been through all this myself and to try to entrench a little bit of a deeper sense of what all these concepts mean. Great graphic, I know. Okay, on to the actual content here. So we're going to start with the Bohr model of the atom, which I'm assuming you have a little bit of familiarity with already. This isn't, like I was saying, this isn't like super foundational concepts only. And it really starts with something called the Rutherford gold foil experiment, which you've probably already heard of in your class, but we'll kind of touch on a little bit here. So essentially what's going on here is this guy, Ernest Rutherford, takes a bunch of alpha particles, which are just 2 protons plus 2 neutrons, which means they've got a positive charge because of the protons, and he shoots them at this sheet of gold foil, which I'm representing with this, with this silly little bronze thing here. And as you see in the diagram, most of them pass straight through and reach the detector that's beyond it, but a couple are ricocheted off to the side or even backwards. And what does that tell us about these gold atoms? Well, for Rutherford, it's that most of the atom is in fact empty space or filled with something that cannot repel the alpha particle. And there's only a very small amount of the atom that is positively charged because it repels the positive alpha particle, where electrons, or the negative charges, fill the rest of that very large space in the atom. So as you can see in my great diagram, most of the alpha particles go straight through, but the occasional one that happens to hit a nucleus, a positive nucleus by chance, will ricochet off. And that's why we observe the fact that most go through, but just a couple are scattered. Okay, capiche. So we get this rough model of the atom, where there's some kind of positive charge and it's very small, and let's place it at the center because that kind of makes sense in a planetary sense. And then the atom is filled, the rest of the space is filled with these negative charges that are kind of just hanging out around here. It's sort of amorphous. There's no real structure. We know it's mostly empty space with negative charges, but that really gets refined by Niels Bohr. So he takes this idea that electrons are kind of scattered throughout this empty space, and he applies a concept from quantum mechanics called the quantization of energy, which really just means that energy exists in distinct amounts. And the implication for that, for the atom, is that electrons will have distinct energies and therefore exist in distinct levels. So on this sort of new Bohr model that you've likely seen before, the electrons are organized into shells based on how much energy they have. So we take this kind of amorphous model and we're adding a bit of structure to it. And this is going to be really crucial for understanding periodic trends, as we'll see at some other point. So going one more step beyond Bohr, how do we sort of refine this a little bit? So let's look at neon for an example. It's an atom with 10 electrons, which you can see in the periodic table. which the Bohr model breaks into 2 electron energy shells. So the first thing to notice here is that each row or period of the little makeshift table that I've drawn out here, it's a bit abridged, but each row or period corresponds to one shell. So this first inner shell corresponds to this first row, and the second shell on the outside corresponds to the second row or period. So lower energy electrons, like the electrons that correspond to this first row, this hydrogen-helium row, are placed closer to the nucleus, while the 8 electrons out here corresponding to that second period are further away, which means that they are higher energy. One thing to note here is that the number of electrons in a shell is equal to the number of electrons in a period. So we've got 2 and then 8. And then, if you will recall, the term we give these electrons is valence, which will become, again, relevant soon. So, to further extend this, we're going to organize the periodic table into blocks, which we call in chemistry subshells. So, within this larger shell of 8, we've got a part of the subshell that comes from the s orbital and part from the p orbital. And again, you've probably heard this before. And I'll cover this in much more depth in a later video, but the key skill to have for now is to be able to place electrons into orbitals in the right order. So, as you can see here, we have the s, p, d, and all the way down here, f subshells, right, which are named for reasons that I don't quite understand, and you don't have to either. But if we look at this, we can see that the S subshell has 2 elements per period, P subshell has 6, D has 10, and the F has 14. And the picture on the right will probably look familiar in a high school or college level chem class, and I'm referring to this picture in particular on the right, where the S subshell has 2 electrons, again corresponding to 2 atoms, that we organize into one orbital, and then P's got 6 electrons, right, because there were 6 atoms, that we place into 3 orbitals. D has 10, so we put it into 5 orbitals, and so on. You get the idea. So here we'll do a couple of examples just to illustrate how we fit the order in which we fill in the orbitals, because that's really important, again, for the next video, which is going to be on periodic trends. So we look at hydrogen, we scroll back up, it's only got 1 electron, and it's in an s orbital, right? So all we'll do is we'll copy down our little orbital line here and then add 1 electron. And you can start with the up-facing electron or down-facing, it doesn't really matter. And we'll label this S. Okay, easy enough. Helium. That's got 1 more electron, right? It's over on the right side here. Although it really kind of could also be placed next to hydrogen, if you like. And again, still just 1 s orbital, but now we've got 2 electrons to fill in. So we'll do 1 up, 1 down. And this is kind of our first major rule, where whenever we are putting electrons in orbitals, any given orbital must contain 1 up and 1 down. So for instance, this doesn't work because they're both up, and there's reasons for that. So yeah, 1 up, 1 down always. Okay, moving on. Nitrogen. So where's that? That is over here in our second row of the table. So we're going to have the s electrons like before, and then really we're just going from left to right, row by row. So if we go left to right, row by row, we've got 1 from H, 1 from helium, and then we go back to the left side with lithium, beryllium, boron, carbon, nitrogen. So how do we organize those? You can see that lithium and beryllium are both in the s block here, so those will get an s orbital. So let's fill in our hydrogen, helium, lithium, beryllium, and label these s as well. And actually, why don't we chuck in a 1s here, because this was from the first period. Put a 1 here, and then a 2 here. So we'll make this one called 2s, which should be familiar also. But now we're sort of transitioning into the P block, right? Because if we keep going across the table, we get to the p. So for that, if you recall, we need 3 orbitals. And the way we're going to fill them is that each orbital has to have 1 electron before any orbital can have 2 within a given block. So like within P or within S or within D. So we've got 1, 2, 3 P electrons to fill. So we'll give each orbital 1. And again, this won't work because this guy got a second one before the third guy got a first one. And this won't work for the same reason. So it's got to be like this. And we're going to label this 2 for the second period, P. Okay, last example, hardest example. We're almost done with this. We're going to look at chromium. So I'll just quickly speed through all the I guess, inner level electrons. So we have this 1s before, this 2s like before. All of the 2p is going to be filled in because we're going to keep going down the table. We've got 3s. That all gets filled in. 3p all gets filled in. 4s gets filled in. And then we're in this new d block that we haven't seen before. And the thing with the d block is that it starts from number 3, even though it's in the 4th period. And there are also reasons for that. And I know I'm saying that a lot, but this is a kind of surface level introduction for now. So let's fill in all that stuff. So 1s, 2s, 2p, what do we say? 3s, 3p, 4s, and then this would be 3d because it's in the 4th period, so d is 3 here. And there's going to be 4 electrons here. So for d, we draw 5 orbitals, and then 4 electrons. 1, 2, 3, 4. Now, this last orbital has nothing right now. And don't get confused yet, but what actually really happens here is the 4s is going to give up 1 electron so that the 3d can have a full... So each orbital in 3d can have 1. And the reason for that is half shell stability. So right now the 3d is half filled, which makes it very stable. And the 4s is also half filled, even after losing an electron. So it's still quite stable. And that happens to be preferable to what we had before, which was the 4s was totally filled and the 3d was not half filled. And total stability, like the 4s has here, is more stable than half shell stability. But in this case, we're trading 1 full shell stability for 2 half shell stabilities. So that kind of equals out to give the advantage to this configuration. And we'll see many more examples of that later. But just to kind of wrap up here, this is taking us towards a discussion of periodic trends, which I feel is really the first challenging topic in intro chemistry courses that a lot of people confuse. But if you understand this electron stuff really well, it becomes much less confusing immediately. Okay, so that's all for this lecture, but